Okay. We are talking about 4.3, the electric displacement, which is named as D, and it is consists of electric field and the polarization of the material. So obviously, this is for us to describe dielectric material as well. Okay, let's go. Okay, so in a material, there are bound charges and free charges. So the total charge or volume charge density equal to the free charge part and the bound charge part. So we we have to consider the bound charge, and by bound charge, we use the polarization of the material and taking the divergence and take a negative signs. We have the bound charge uh, part. Uh, of course. So by the very beginning, we know the Gauss law that we take divergence of electric field and times the epsilon naught will equal to the total charge. So now we just replace the charge density by bound charge, replacing this one. So we just rearrange it, and we have the free charge density on the right hand side and everything collected within the divergence. So here we consider epsilon naught is just simply a constant, just move in. So now this become a new vector. Look at that. This is a combination of two vectors. One is the electric field, one is the polarization of the material. So we define these new things. We say D, and later on we will name it as a uh, displacement. Okay, so here, look at this one. In general, these are three vectors. So electric field and polarization is not necessary along the same direction. So these three are not necessary all going to the same direction, and in general, it's not. So just be aware of it. So now this newly defined D vector links with free charge. Of course, look at this one. So taking the divergence of D just simply equal the free charge density here. So we can use the same technique of the divergence theorem again. So now this D taking the surface integration on a closed surface will be the free charge enclosed. So this is F and enclosed here. So now, in many situations, no bound charge information is provided, but free charge information is given. So D is useful in this case because we just have the free charge information. We just deal with D without taking care of the polarization part. Okay, so let's take a look at the example 4.4 here. So if we consider a long straight charge with a line charge density lambda, so this is a line charge and is a straight line, and so the charge density is lambda. Since we got a taste that we can use the Gauss law, so we choose a similar Gaussian surface like we did before. But the the thing is here we got a different situation because this line charge is enclosed in a rubber insulator. So now, what does it mean? So just like an electric wire, we have some rubber cover a wire. Okay, so now we got something outside is just plain space or vacuum, and within is a piece of rubber. So now it will be difficult to deal with. So now we just the problem will ask for to find D everywhere because it doesn't care about the material that contribute to the induced dipole whatsoever, making the thing polarized. So we just take care of the D using the previous result using the simple uh, Gauss law, and we just take D have the surface integration through the closed surface equal to the enclosed free charge. So now, because this material is dielectric, it can be reduced dipole whatsoever, but we don't care. Here, because this relation tell us we only we need to know about the enclosed free charge. So here, the only free charge is the line here. So now, so the left-hand side, this is a closed surface. So since it's a wire, so we choose the cylindrical coordinate. That'll be easier. So we choose the Gauss surface as cylinder. So now we have the surface area, which only consider this part, the cylindrical part. So it's 2 pi s times L. So if we choose the Gauss surface with length of L and times the d, this here we replace the vector into just the constant part. So equal to the lambda times L because the line charge density is lambda. So times L is the length of it. So now we got the value of d is this one. And we also know the field is pointing out. So d is pointing out. So along the s cap direction. So regardless inside or outside the rubber, it is still the same thing. This d value remain unchanged. But, well, if we want to know something outside the wire, just actually replace our electric field. We can solve the electric field by just d minus p and divide by epsilon naught. So we can have the electric field outside the rubber. So that should be it. Simple enough. Okay. So in example 4.4, surface bound charge was not discussed. So in the example, we don't talk about the surface bound charge. Indeed, there should be a surface bound charge in that case. Gauss law can be applied on the boundary. That becomes some problem because we cannot choose the surface right at the boundary. Ideally, the polarization has value in the dielectric material, of course, because the induced dipole moment and make it polarized. And however, when you across the boundary to the vacant or space, it will suddenly turn to zero. When you go right outside the material, that becomes a problem because when we take the bound charge and we know the polarization will suddenly from some value become zero. So this divergence will become infinitely large. So means this bound charge is infinitely large. This is not possible. So in reality, such sudden change is not possible. Okay, infinite charge is not possible anyway. So in fact, the polarization is fastly but smoothly changed to zero. So this divergence will be finite. So actually, it will give us tells you there is really some surface charge anyway. So this process change rapidly but smoothly, so not sudden change make the divergence or the derivative become infinitely large. So this tiny region is very thin and but still smooth enough to have a better behavior of the function property. So then the Gauss law is okay. Everything works as expected, just like we discussed. This is just something mathematical consideration and the reality check of what will happen. So that's just something to be aware of. Okay, now, so because we have the relation that we see in the electric field, we take the divergence, we got the total charge density. And we take the divergence of D, we got the free charge density. Okay, so this is something very similar. So we are quite attracted by this property. And also because of divergence theorem, we can take the surface integral over a closed surface. The D will equal to the total charge enclosed. And electric field, or total free charge enclosed. But electric field will be total charge enclosed with just one coefficient here. So indeed, they are really look alike, and their formulation are also very similar. However, D is very useful when solving dielectric problem because we don't need to worry about the bound charges, right? So, but there's no D and free charge density based Coulomb's law. In other words, we cannot write things like this. This is a simple Coulomb's law, but this is not true. So, in other words, D is not the free charge is not the only source of D. Okay, so this is very important to know. We do not have this relation. Okay, and in fact, when we take consider we take the curl of electric field, it'll be 0. Okay, but when we take the curl of D, we actually end up curl P. And in general, curl P is not necessary to be 0. That's the thing. So even though the relation looks very much alike, but they are not the same. D is not another form of electric field. So be careful. Okay, so now, oops, sorry. So now we are going to take a look at some interesting video here. Okay, so now. Okay, so here we got two videos to see. The first thing is
Despite what it looks like, this is not a magnet. Actually, it's something much more exotic. And the invisible field it emits is easily seen using this 5x5 detector array. But what exactly is the grid detecting? This video is sponsored by Factor Meals. Thank God, because I can't cook. Magnets are underrated. Using an invisible Jedi magnetic force, these little objects attract ferrous material, and their attraction is permanent. It's honestly remarkable, but is there
okay. This video is kind of long, so I would rather you watch it yourself. But anyway, it demonstrates some very interesting things, right? Here he take a piece of interesting looking things and approaching to a detector and actually showing that there's something influence the detector array. And in fact, this piece of thing is called electorate. This is the word electorate. Okay, and this is actually something carry permanent charge. And just like a magnet carry magnetic field, even though we are not talking about a magnetic field yet, but we know magnet, right? We know magnet can actually attract material, iron material. So there's a similar thing called electorate, not magnet. Electorate actually attract charges. It carry a permanent charge, just like a magnet. So this video actually tells us this thing doesn't exist, and he studies some of it and how to make it. So this is kind of an interesting video, and eventually he make this material and into some real things. So this real thing actually can and also this guy make a detector. The detector, I don't know where is it, so we'll check. So he make his own detector here. Okay, this is the detector.
So what is ClickUp? ClickUp is an all-in-one productivity software where you can manage everything and anything.
hour or so the wax had cooled and
He make a detector to detect if there's some electric field in this region. So by that, he can turn on the.
and I was thrilled to test out my new static
turn on the
object.
LED here.
Okay, so here's the electret. If I made this correctly, there should be a permanent static field. Let's see what it does. Nothing yet.
This is not working here. So, but
Nothing.
anyway,
Here I pulled out my Van de Graaff and placed it over. Ooh. Okay. Oh, look at that. So as I point my finger at the generator, it loses charge.
Okay, so that's it. So eventually he made the electrolyte and using certain complicated method and make sure that piece of material actually at the beginning carry the charge and can attract anything just like a magnet. This is why you know. And uh, you should go through the video because this is fun to watch. It actually using a wax and with some kind of uh, polarize the molecule, and actually with it when the wax is trying to solidify it, become solid, and during the process he apply high voltage in between these two sides, and in the wax he make some of the polar molecule and mixing within the liquid type of the wax. And then during the cooling process, the wax will become solid. And because he applies strong electric field, so the polar object will be polarized into a permanent dipole and accumulate surface bound charge on both sides. So he can work, this piece material work as a permanent dipole moment. Okay, so this is the entire thing. This is really fun to watch. So please go check it. This is good one. Anyway, so all right, and there's another video is talking about the this kind of material, just this one, the electrolyte. And oh, sorry. Before that, actually, our medical mask, or even N95 mask, are made of similar things that contain a permanent charge. So it actually attract small particle like a virus, like a dust, and to accumulate, attaching to the fiber of your mask. Your mask. This is how we prevent breathing the COVID-19 virus, because at that time we just wear a mask. So this is how we actually using the electrostatic field to attract small particle, then protect us a few years ago. Anyway, so now the second video is actually talking about bar electrolyte, very much just like the previous guy did. Okay, this is a piece of material which is polarized. Okay, so what will happen is actually
We're going to take a look at the bar electret, which, as the name implies, is sort of the electric analog of a bar magnet. And the analogy is that while a bar magnet has a uniform magnetization vector within its volume, a bar electret has a uniform polarization vector within its volume.
So it says so. Just like this is very similar to a magnet, but instead of later on we will say the magnetization vector, but this one is polarization or dipole moment accumulate within the volume and pointing one single direction.
While a lot of materials will only have a non-zero polarization if you apply an external electric field to them, there are materials that have this sort of built-in polarization, and these are the materials you could use to make one of these electrets. So specifically what we want to do is think about how the field lines of both the electric field E and the electric displacement field D produced by this electret look both inside and outside its volume. And it turns out that this is quite an interesting thing to do because it illustrates some important differences between these two fields, and also illustrates how the standard relation D equals epsilon E doesn't always apply. And in fact, you can have your electric fields and your displacement field pointing in almost opposite directions. Now, as it turns out, the displacement field is actually a little bit easier to understand. So we're going to start with trying to sketch some field lines of D. And in order to do that, we just need to remind ourselves of some important equations relating to the displacement field. So let's just note down some potentially useful equations. A good place to start would be the definition of the displacement field. It's defined such that D is epsilon naught times the electric field plus the polarization vector. Now, if we're trying to sketch field lines, we need to know about things like the divergence and the curl of D as well. Now, D has this very useful property that its divergence is given by the free charge density in the system, where free charge is just any charge that's not a result of polarization. Now, in this particular system, you will have charges accumulating in certain places on the electret because of the polarization of the negative and positive charges, but there are no free charges. Everything is a result of polarization. So in this particular case, the divergence of D is going to be 0. Now, what about the curl of D? What can we say about that? Well, take equation 1 and just take the curl of both sides, and you find that the curl of D is epsilon naught times the curl of E, and then plus curl of P. But if we assume that nothing is time varying, in particular we don't have any time varying magnetic fields around, then one of Maxwell's equations tells us that the curl of E is just 0, and therefore the curl of D is exactly the same as the curl of P. So what do these equations tell us about the shape of the field lines? Well, equation 2, the divergence being 0, tells us that there are no sources or sinks of D in this particular system, and the only way that that can happen, unless D itself is 0 everywhere, is for the field lines to form closed loops, so that they sort of don't start anywhere, don't end anywhere, they just form these loops. Now that already sounds very reminiscent of the field lines that you get produced by either a solenoid or a bar magnet, right? Your B field lines form closed loops. And we can take that analogy even further and notice that equation 3, curl D equals curl of P.
Okay, this is kind of long, so we are not going to go through it. And pretty much, this guy got a very clear explanation. And pretty much we use the same old trick, got a loop and try to do the integration and that kind of things. So eventually this will tell us how to deal with it. And we eventually can draw the D, how the vector field will look like. The D is actually a field. So, and also we can figure out what the electric field will look like. So the interesting thing is your electric field is actually going the other way within the material. So that is some very interesting result. So this worth your time to take a look at it. So this guy explained pretty much in very much detail. So go ahead and check it. All right. So let's go back to our lecture. All right then. And all we have here. There you go. Okay. So anyway, so in that case, our uh, D taking the curl is equal to the curl of P. So this is very different from electric field. So definitely do not confuse or uh, just using the electric field and to apply to D. This is not likely to happen. Okay, so now. So there's a problem in the textbook, so probably you want to go ahead and check a look at it. And pretty much this is what you are going to have the result and the video talking about what is the electric field looks like, what is the polarization will be, what is the uh, D looks like, the field will look like. Anyway, so and because the electrolyte is just a bar that are made for polar molecule and the total charge is 0. But because this is made within the high voltages, so they are polarization very uniformly distributed and there are surface charge here accumulated, but there's no free charge, of course, because nothing move around. So the surface charge accumulate on both sides. So that becomes just like a magnet. but instead this is electric field showing. Okay, so there's no free charge anywhere. So because our divergence of d equal to the free charge volume density, so if the only source of d is free charge density, then the only possible d is 0 everywhere. See that? Because we write this thing down, and if d is really similar to electric field, that should be the source of d. The free charge should be the source of d. But this is not possible because when the field, because in the electric ray there's no free charge, so d must 0 everywhere. So electric field equal this thing, and but when this is outside the electric ray bar, the electric field is 0, but this is definitely not true. So the assumption that Zo f is the only source of d is not right. So in fact, because of the curl of polarization of the material is not 0, this thing actually contribute to the polarization actually contribute to the d. Okay, so since curl of d not equal 0, no scalar potential like v or e can be applied. So that's the thing to be very careful, to be aware. All right, so that's why this title is deceptive parallel, because electric field and the d are very similar in some way, but they are not the same. Be careful. So when solving a problem to obtain d, use geometry, symmetry, and Gauss law as well. Follow the symmetry, and the curl P is 0. If no symmetry, find another way. Okay? Just keep in mind, D is not only determined by our free charge density. Okay? And the later part is the boundary condition, because in previous chapter we talked about the boundary condition for E. So this is something you should be aware again. So on the boundary, if there is surface charge, we separate the electric field. This is the electric field above and below. Okay, so we separate it as the parallel one and the perpendicular one. So using the symbol perpendicular and parallel instead. And also the field on the upper or above median and below median. And also we need a surface normal vector. Okay, so now we know the boundary of electric field is actually telling us the electric field on the top and the bottom. For the perpendicular components, they are having a relation that the surface charge density will take a rule here. But the parallel electric field is actually continuous. So below material here, the lower material here has a parallel electric field will continuous along the boundary. So the above parallel component is identical with the below electric field component. But D will be slightly different now. So D is by definition is the surface integration is equal to the enclosed free charge. So since if the boundary has free charge, okay, so then we will take just like the same old trick, take a small pillbox to do the same thing, and we will get a result that the perpendicular direction will give us the free charge here. So this is really simple, as we can see. But on the tangential or parallel component will be very much different because of this curl relation. So this gives us the another boundary condition, which the difference between the above and below parallel component will be the difference between the above and below polarization components. That's it. Okay, so that is the important things to be aware of. Okay, but a very general configuration can be very confusing. Even though in the textbook, just a very small paragraph, you probably should go through it. And so here, I just write things down and showing you what will be. All right then. So you got the D on both sides and D above, D below, and we have the a perpendicular component along the normal direction and a parallel component and below parallel component and perpendicular component like this one. And you got a surface charge density. So if this part, the above part has a polarization along this direction, since it is not necessarily along D or electric field, it doesn't matter, just one direction. And of course, you can split it into the above parallel direction and of course perpendicular direction as well. But because perpendicular direction component is not going to be used, so we are not going to talk about it now. And the below part, you also have the polarization direction and the parallel component here. So the above parallel component, this one or this one, and minus parallel component of D at the below. So it will be vector pointing this direction. So this vector plus this vector will be equal to this brown looking vector. And that's the difference between the above and below polarization parallel component. The above parallel component here and below parallel component and take a negative sign, so it goes this way. So that is the difference. So this will be satisfying this relation. This is how it is, and this is what written here. Okay, so that's it. You can check it. So because in the textbook it's just written in the text, and I just try to make a figure that you understand better. So if the parallel component on the above part is 0, so your parallel component will be just determined by the below part. That's it. So in general, you will encounter things like this anyway. Okay. And the last part is about the crystal ambiguity. This section discusses about the choice of pairing of the positive and negative charge of the ionic crystal, because ionic crystal like sodium chloride and NaCl is actually you can freely choose a different direction, and they are equal spacing. The sodium and chlorine are equal spacing everywhere, so you can pick any one of it, but you will figure out the the charge left out is on the boundary, and depending on how you choose, you will choose a different part. You will have something left on the boundary. So this undetermined part of the thing looks like it will make problem of how you choose and make different result. But in this part of the text, it will tell you not that important. But anyway, please read it yourself. Okay? So that should be it.